Oh, got it. So let's imagine we have a doublet at the origin. So we have our values, and then we place a doublet right at the origin. I'm going to erase this axis here because we're still not ignoring the origin. Is just to understand where we will be in an x and y axis. We have doublet here, so we can already start drawing a. Actually, no, let's keep it like right now. It's only a free stream, so we have a free stream moving in this direction from left to right, and the velocity is u infinity. We have uh, different equations in our case. So we have our phi is u infinity r cosine theta plus mu divided by 2 pi cosine of theta over r. Then we have our radial velocity, and we're doing all this in a radial unit. U infinity cosine of theta minus mu cosine of theta divided by 2 pi r squared. And of course, our tangential velocity, which is equals to negative u infinity sine of theta minus mu sine of theta divided by 2 pi r squared. So now let's say that we have a stagnation point when r is equals to a. Our stagnation point means that our ur is equals to 0. So we have to take this and put it equals to 0 when r is a. So substitute r with a. So let's solve it for our mu here. So we get u infinity cosine of theta times 2 pi a squared divided by cosine of theta. So we simplify this to cosine of thetas, and we get u infinity 2 pi a squared is equals to our mu. And of course, it's valid for both uh, r. Well, actually, it's r. So never mind. I was gonna say x is equals plus or minus a, and y is equals to 0. So we're talking about moving on the x and y axis, not on the on the x-axis, not on the y-axis. So if we go back to our drawing, what do we get? Well, we get a circle like this, but centered around our doublet. I want to say it's about here, where there's no movement. So our flow will get here, and then we'll move along our um, circle. Of course, I'm drawing a little bit of distance between them, but they're actually the same line. And then we can inside we can have any sort of movement of of flow. The idea is that, however, on the outside it has to match this movement here because there's no slip condition. So we have something like this, and then in the inside it has to match. Sorry, in the center they have to match. So we're gonna have something like this. Let me draw a little better. There we go. As you can see, these match the outside boundaries, the outside velocities, and they match each other's velocity. They go in the same direction at the center. But the idea is that we can replace this streamline outside, or this line exactly, with a solid boundary. So instead of imagine to have a doublet, we can imagine we have a solid surface, an object. So we have an object in our flow. This makes our, imagine to erase this makes plotting the reaction of a a fluid will act around an object very easy. So it will be something like this, of course. There we go. Now, if we go to our radial velocity, we said is equals to 0 when it's at this point here. But what is our tangential velocity? Well, let's calculate it. So theta will be what? Well, if we've said that we were the origin right here, then our point here and here will be pi and 3 pi over 2. So let's substitute a pi over 2. Let's say that theta is equals to pi over 2. Then what do we get? We get a negative u infinity. Sine of pi over 2 is simply 1 minus mu. We just said sine of pi over 2 is 1, so 1 divided by 2 pi r squared. But we also said what is mu at this point. We found mu thanks to our radial velocity. And we said it's equal to this. So let's take it. Oops, not erase it. Let's take it and duplicate over here. So we have u infinity minus this divided by 2 pi r squared. R is a in this case, of course, because we are at a distance a, a radius a. So we all these things simplify, and we get negative 2u infinity. Now, first of all, I want to go over this sign. I want to go in order. Why a negative? Well, because when we're looking at our problem, we always imagine that a positive um, value is going clockwise, counterclockwise, sorry, counterclockwise, while at this point here, we're going clockwise. So it's going to be in the opposite direction as what we count as clockwise. Why do we count clockwise as positive? Well, because of the right hand rule. If you point the thumb towards you, then the rest of the hand will point in the counterclockwise hand. So this is negative because of this. Why 2 though? How does this velocity increase? Well, I want to explain this using conservation of mass. So if we go back here, we can see that we can imagine that there's other lines up here and they still go untouched. Okay. The idea behind it is that this area between the two, well, in our case the height because we only have one dimension, um, is unchanged. So this one is unchanged wherever I take it. Of course, they always take the same length. So, or set of course in one dimension, the height does not change across all these points. So it's all the same. However, here, the distance between these two lines is not the same as the distance between these two lines. But the problem is that we said that our, I can say that the material derivative of our density is equals to 0. So it's incompressible. So how is it possible that we have a smaller height? Where is all the mass going? Well, the way I want to explain it is by using mass flux. So if you remember, the mass flux was the integral of our density times our velocity vector times dA, or in our case just the y, because we're going from we're going based on height. Well, the density does not change, so this one we can take out. The height decreases, so it goes down. So what is it has to change? It has to increase to give us the same mass. Of course, we're talking about the mass flux, but you get the point. So, oops. So the velocity increases, and that is what we see in here. In fact, it doubles. Why does it double? Well, because actually the height then halves, and there's no change in density. It's still incompressible flow. This happens both at the top and at the bottom of our flow. Now, of course, if we were to plug in values for our bottom, if we go back here, here will be -1, which will make positive. It will be -1, which will make this thing positive. So we have a positive 2, positive 2 u, not well, positive 2 u infinity, not negative like we have here. We would have positive, because in this case, it's going in the same direction as counterclockwise. All right. So we can just say that the magnitude of our velocity is double or doubled. That being said, we can find a pressure coefficient by calculating the difference between the pressure at our point and the pressure at point at infinity divided by our dynamic pressure. Now, I want to remember that the dynamic pressure is the pressure due to only the um, velocity of flow, and that is due to the fact that it's just moving around the place, and we have our velocity at infinity. So what do we have here? Well, we have 1/2 rho u infinity squared minus 1/2 rho v squared divided by 1/2 rho u infinity squared. Now, as you can see, a lot of this stuff is the same, so I'm going to cancel out everything that is in common. And what do we get out? We get a u infinity squared minus v squared divided by u infinity squared. That I can rewrite as 1 minus the ratio between the squares of our velocities. Okay, this can be plotted, of course, and we have our plot that looks a little different than what you're probably used to. So I'm going to do something like this. It starts at 1 and it goes all the way up to -3. Now you'll see why. Well, at our initial point here, what is our v? Well, v is equals to 0 because we have no vertical velocity. I mean, you know what? I might have explained that a little wrong. So this is the pressure that we have at our point, and this is the pressure that we have at the point of infinity. Maybe I should change it's okay. So our v here is 0, so we can say it's equals to 1, because of course we have 1 minus the ratio of the squares. U infinity is here, square, okay. So now we said that our point, initial point on the x-axis, we have v is equals to 0, so it's just going to be 1. However, our v will reach a value of 2u infinity. So our maximum value will be 1 minus 2u infinity squared divided by u infinity squared. So these two would simple out, but we will get 1 minus 4, so it's equal to -3. So we would go up all the way to -3, and then down all the way to 1 again. And this is what happens for our pressure coefficient. And of course, we have the same thing on the top and the bottom, because of course, even though the velocity at the top is negative to v0, we are squaring it, so we're just taking the magnitude. So it simplifies everything. However, in a real flow, even though we have this curve like this, it goes down here and then it stops going down and it goes like this. You may wonder, why is that? Well, it's simply because the fluid does not actually keep touching um, the fluid does not go actually all the way down to have only a horizontal component, and so there are vertical components still present, and that is called due uh, uh, to some areas of rotational, and it detaches, but that's not something we have to worry about right now, so we shouldn't worry. Now, I want to say, what if inside that doublet we added a vortex? So our formula for vortex is gamma divided by 2 pi and times our theta. You know, gamma is like this. It's a little hard to draw, to write. Okay, so if we were to imagine a vortex in our object, it means that our object is actually spinning, right? Imagine just a cylinder spinning. Well, how does that do anything? Well, then we have our phi is equals to u infinity r cosine of theta plus cosine of theta divided by r times a squared plus our vortex. We just add it linearly. So this part here is due to uh, the double uh, doublet, and this part here is due to the vortex. Okay, well, from this we can derive the radial component, which is equals to always u infinity divided by 1 minus a squared over r squared times cosine of theta. And as you can notice, this one, the radial velocity, is the same thing that we had. Actually, I probably didn't write it before, but it doesn't change if we have a vortex or not. Because, of course, the vortex does not have a radial component velocity. It only has a um, tangential component. So how does our tangential velocity change? Well, we have always u negative u infinity times 1 plus a squared divided by r squared times sine of theta plus our gamma divided by 2 pi r. Well, I don't know if you remember what u, oh, infinity d theta, u theta is equals to 1 over r d psi d theta. Okay. Oh, I think there's no, yes, it's correct. Okay. Um, okay, so this now changed. Well, once again, if our radius is equals to a, then this part here equals 1, and this part here equals 2, so we still have negative 2 u infinity times sine, oh, sine of theta was again we said at pi over 2, so just 1, plus our gamma divided by 2 pi a. Again, because we said we have a, r to be a. Okay, so now, oh, actually, you know what? I'm gonna keep the sign of theta right now here. Okay, now we want to set our tangential velocity to be equals to 0. So when is that actually happening? Well, again, of course, our radius will be a, so we don't have to worry about that. We have 0 is equals to this thing here. So I'm just gonna copy and paste it. So we have what? We have that sine of theta is equals to gamma divided by 4 pi u infinity times a. This is very important because now our angle, the position where our stagnation point is, depends on theta. So for example, if we have our gamma to be greater than, sorry, to be, let's just say that gamma divided by 4 pi u infinity a is equals to 0, then we have no rotation, we have no vortex, so we don't have to worry about it. We just have our usual object and then stagnation points at the usual stagnation points. So going here, going this way, moving this way, and then the usual for everything else. Then at one point becomes less and less, it becomes nothing. Okay. However, if we have our gamma divided by 4 pi u infinity be greater than 0 but less than 1, then what do we have? Well, we have our still our object at the center, then our full coming from the left side. Okay, what happens? Well, in this case, our rotation is present, is positive, so it's going to go in this direction, but it's small enough that our sine of theta will yield a theta to be in between 0 and pi over 2. So we can say that it's going to be, well, actually it's going to, it would be positive, so yes. 1 second, let me just make sure that I make mistakes. Okay. Um, yeah, so we have our uh, stuff to, let's start to do this. Well, actually, it just, we say there's no separation, so it just keeps going like this. But since we have rotation, it means that it actually follows it more, and then it goes up here. And then on top, we have something that touches and leaves like this. And then for some other flow coming like this, it just hits it, and then it's gonna have to go down and do this. So our theta will be between 0 and pi over 2. Now, the fun stuff begins. I'll just say that. When we have a gamma over 4 pi u infinity a equals to 1, well then our theta has to be equals to pi over 2. So once again, we have this time we have a stagnation point at the top. So we have something like this. More like, sorry, okay. It just goes down and then we have stuff coming up here. Maybe a better drawing would be something that does this, because it's also a stagnation point, so it doesn't move that exact point. And this is pi over 2, of course. Now, what if instead our gamma surpasses 1? Well, then our sine of theta can never be greater than 1. So how can we do it? Well, in that case, we have to go back to our radial velocity and see that our r cannot be equals to a anymore. It has to be equals to something else. Because, well, then we can max out our sine. You know what, let's copy it from here. So we take our maximum value for theta, which is what was happening here. We started turning it in the counterclockwise direction. We started rolling fast enough that it reached a value equals to this, and of course the ratio is 1. But then we go past that. Well, the sine cannot increase anymore, so sine of theta will still be 1, therefore theta will still be pi over 2. So in our object, we're still going to have a stagnation point up here. I remember this, we were talking about the angle. But now, what can we increase? Well, what we can increase is our r. R can increase. So this still has to be equal to 0 because we should have no tangential velocity. So I have minus u theta divided by 1 plus a squared. Now I'm going to write r squared because that increases. Sine theta is equals to 1. So plus our stagnation, our gamma by 2 pi r. In order to make this 0, r has to increase. It has to go past our a value. Okay, so if it goes past our a value, it means that actually we have something that looks like this. Actually, it was a very bad drawing. I'll do it again. Okay, so where do we actually have a stagnation point? Well, we have it here. As you can see, it's still along the pi over 2 line, but now r is greater than a. And it makes our equation right here still hold. So if we rotate it up, our our stagnation point can lift off the surface of our object. Now, I like to think of it as the fluid in here being like an additional part of the object due to some viscosity and stuff like that things, and it makes it rotate so fast that it cannot really keep up. And so the only thing that can keep up is going to be up here. However, now that a um, we have a pressure there, we can calculate the force due to this pressure. So the surface of our pressure times our normal vectors over an area. And so we substitute our pressure for our differences in pressure. So negative P minus P infinity um, and hat dA. And so we have, of course, we can substitute what we found earlier for our pressure coefficient. So 1/2 uh, rho u infinity squared times our Cp and hat dA. Now Cp will have two components, of course, the I component and J, sorry, Cp will only have a J, actually Cp is a coefficient, so it's nothing, but it ends up giving us a value of negative rho, u infinity, uh, and then gamma j hat. So we only have a force acting along the j hat direction or vertically. Now, what does this make you think? Well, it makes me think if I roll something fast enough in a counterclockwise direction, it will go up. Sorry. Um, if you think about this, you can imagine um, a roll of like toilet paper, and if you spin it fast enough, it can go up to this force. Now, of course, we imagine there is no gravitational force in this case, but it can go up if you spin it fast enough. This is actually being done in some boats that have some um, rotating cylinder, and if they rotate fast enough, they can actually create a force that pushes the boat forward or backward depending on their direction and on the flow and of the thing. In fact, the higher flow will make it have a higher force, and then um, a higher circulation, of course, will make it go higher. However, you have to remember that the lift, which is, of course, this becomes a lift, is going to be perpendicular to our uh, flow velocity, flow direction. And this is called the Kuda-Joukowski, I apologize if I am butchering the name, theorem. And another force that we found was our drag, which was zero. We said our drag was zero, there was no drag. So, and that is our D'Alembert's paradox. We have no drag because, well, our flow just passes by the object. There's nothing holding back. We said there's no friction. The Reynolds number is high enough that we can just ignore the no slip condition. And there is a paradox. This works for any closed shape in a two-dimensional potential flow, and you can see this in a lot of things. For example, you can also see this in sports. You can see this, for example, in soccer when you kick a ball hard enough, or football, depending where you're from, what do you call it. Um, and then you can uh, see this in baseball, for example, or in golf balls, or in many other effects. Actually, tennis as well, just not as much, probably. Remember that I'm gonna put a link on my in the video description that brings you to a PDF where I'm explaining all this stuff in a written way in case you prefer.